So we have a black hole, and we have an accretion disk. And as we'll see shortly, there's an inner edge to this accretion disk because of stability issues. You can no longer have stable circular orbits inward of some location. We'll see what that location looks like as a function of the spin of the black hole. But here's the accretion disk, and this is the outer edge of the accretion disk, if we can really define such a region. But so we want to get a sense of the distribution of energy for circular orbits. So we have a function of r. At every r location, there is gas plasma that's rotating around, and it has energy and it has angular momentum. We want to get a sense of how energy and angular momentum depend on r. So we need our conserved quantities. Energy is associated with time independence, and the angular momentum is associated with things being independent with the angular coordinate, which we can call phi. And then we get our conserved quantities from, we're not going to rederive these things, but they're derived in the relativity course. So energy, the conserved quantity that we call energy is, we need a scalar. So it's a scalar associated with two vectors. There's actually a minus sign. Here, this quantity is a Killing vector associated with time independence. And so what we get there is 1 minus 2m over r, where we've ignored g and c. Otherwise, this would be 1 minus 2gm over r c squared, if you remember. We'll just make c equal to 1 and g equal to 1. And then here we have the time derivative t dot, dt by the proper time, plus 2m times the spin value, which goes from 0 to 1, are actually, 0 to 1, we can put the minus sign for co-rotation and counter-rotation, which we'll discuss in a moment, phi dot, and the angular momentum is obtained from a different Killing vector, psi a, associated with independence of phi. Right, so we're talking about a rotating black hole, and we're dealing with the Kerr metric. So these are conserved quantities associated with this Kerr metric in Boyer-Lindquist coordinates. Okay, and so PA is just a 4 vector, right? That's just a four momentum vector. And so when we replace t dot and phi dot, right, derivatives of time and phi in Boyer-Lindquist with respect to proper time from the Kerr metric, we're not going to go through all of that, then we get the distribution of energy and angular momentum as a function of the radial coordinates. So, and of the mass of the black hole and of the spin. So the energy looks like r to the 3/2 minus 2, the mass of the black hole, times r to the 1/2. And then we have a plus or minus, and then the plus is for, so the black hole is spinning, so it has some non-zero a value. So let's say it's rotating that way. The plus sign is for gas that's rotating in the same direction. And the minus sign is for gas that's rotating in the opposite direction. And there's a fundamental difference, which we'll discuss soon. A m to the 1/2 over r to the 3/4, r to the 3/2 minus 3, the mass of the black hole, r to the 1/2, plus minus 2 spin m to the 1/2 to the 1/2. Okay, so you could plot that as a function of r, choosing a disk that co-rotates with the black hole, where the gas co-rotates with the black hole, or that it counter-rotates with the black hole, and finds the distribution of energy, and it sort of increases as you go further out. And then we could do the same thing for the angular momentum. And here we have plus minus m to the 1/2 times r squared. Then we have minus plus 2a m to the 1/2 r to the 1/2 plus spin squared divided by r to the 3/4 r to the 3/2 minus 3m r to the 1/2 plus minus 2 the spin m to the 1/2 all to the 1/2. Energy and angular momentum are related to each other. So again, plus is co-rotation and minus is counter-rotation. And we can call the differences in energy. So the gas moves inward and it goes from one radial location to another, and there's a difference in energy. And we can talk about delta E, and we can talk about that as the work done. We can refer to that as the work done, as gas here produces a torque on gas further out, allows it to lose energy and angular momentum. And so we could sort of figure out what that work looks like. And so I've done this calculation, and here is the result. So you're looking at, this is a co-rotation. So this is the spin of the black hole. It goes from 0 to 1, but now I've put co-rotation where the disk rotates with the black hole on the right-hand side, and counter-rotation this way where the gas and the disk rotates in the opposite direction. And what you notice is that the work that you need to do to get plasma to move inward increasingly becomes greater as the spin of the black hole increases to its maximum value, which is really more like 0.998. And so it's easier to extract angular momentum in counter rotating accretion disks.